Welcome to Brain Vision.
Okay, so we can apply the energy balance equation for this question. So we have E dot in is equal to E dot out. If we expand it, we have W dot in plus M dot in times H1 plus V1 squared over 2 is equal to M dot times H2 plus V2 squared over 2. W dot in here is the power input from the electrical work, okay? And M dot here is the mass flow rate for the air, okay? Which is the one we're looking for to determine in this question. And H1 here is the initial enthalpy for the air. V1 here is the inlet velocity. H2 is the final enthalpy of the air. And V2 is the outlet velocity. If we do some arrangement here, we have M dot is equal to W dot in over H2 minus H1 plus 1/2 V2 squared minus V1 squared. So we know H2 minus H1 can be equal to Cp times T2 minus T1. Cp is the specific heat for the air and at a constant pressure. And we know T2 here is the final temperature, T1 is the initial temperature. So therefore we have M dot is equal to W dot in over Cp times T2 minus T1 plus 1/2 V2 squared minus V1 squared. And then we know in this case the inlet velocity of the air is negligible, which means that V1 is much smaller than V2. So we have V2 squared minus V1 squared is approximately equal to V2 squared. So now we can use a new equation, which is M dot is equal to W dot in over Cp times T2 minus T1 plus 1/2 V2 squared. So we know the power input is about 1500 watts, which is 1.5 kilowatts. And the specific heat for the air at a constant pressure is 1.005 kilojoule per kilogram times degrees Celsius. And the final temperature is 80 degrees Celsius. The initial temperature is 300 Kelvin, which is 27 degrees Celsius. And the outlet velocity is 21 meters per second. So now let's plug in back to the equation to determine the mass flow rates. So the mass flow rates can be equal to W dot in, which is 1.5 kilowatts over Cp, which is 1.005 kilojoule per kilogram times degrees Celsius, and then times 80 degrees Celsius minus 27 degrees Celsius, and plus 1/2 times 21 meter per second square, and then we need to divide it by 1,000, which is times 1 kilojoule per kilogram over 1,000 meters square per second square. Okay, the reason why we do use such conversion here is because the unit for the mass flow rate is kilogram per second, and the unit for the power inputs is kilowatt, which is kilojoule per second. So therefore, what kind of units we need to get divided by the kilojoule per second to get a kilogram per second. So I will show you what kind of unit is that. So first, we know 1.5 kilowatts units is kilojoule per second, right, which is kilowatts, and then divided by the mass flow rate unit, which is kilogram per second, and this can be equal to kilojoule per second times second over kilogram. As you can tell, second can be cancelled out, and this will give us kilojoule over kilogram, which is kilojoule per kilogram. So therefore, the whole term here need to have the units kilojoule per kilogram. Okay, so that's why we need to convert meter per second squared to kilojoule per kilogram. And so eventually this will give us the mass flow rate is about, let me write it down, 0.0280 kilogram per second. For the next question, while we know the outlet volume flow rates, which is V2 dot here, can be equal to M dot over rho 2. Rho 2 is the density of air at the outlets. We know M dot is the mass flow rate. Okay, so we know rho 2 can be expressed as P2 over RT2. P2 is the outlet pressure, R is the gas constant for the air, and T2 is the final temperature for the air. So if we do some arrangement here, eventually we have V2 dot is equal to M dot has RT2 over P2. So when the mass flow rate is 0.028 kilogram per second, and when the R is equal to 0.287 kilojoule per kilogram times Kelvin, when the final temperature is 80 degrees Celsius, which is 353 Kelvin, and the outlet pressure is 100 kilopascal. So now let's plug in back to the equation to determine the volume flow rates at the outlets, which is the volume flow rates at the axis. And so V2 can be equal to M dot RT2, which is 0.0280 kilogram per second times 0.287 kilojoule per kilogram times Kelvin. And then times 353 Kelvin. And divided by 100 kilopascal. And this will give us the volume flow rates at the axis is about 0.0284 meter cube per second. And these are the answers for this question.